This work introduces ChicGrasp, a robotic system designed for handling delicate and irregular bioproducts, in this case, chicken carcasses. To understand the motivation for our work, we need to look at the poultry processing pipeline. This flowchart outlines the various stages from when birds arrive to their final packaging. Our focus lies in the chilling and rehang stage, highlighted here, where the chilled carcass must be rehung onto overhead shackles for further processing. This task, while seemingly simple, is physically demanding and repetitive. As seen in the video to the right, human workers are required to grasp both legs of the bird and hook them onto the moving shackles. In high-volume facilities like the one shown at the bottom left, workers perform this action hundreds of times per hour. This leads to fatigue, injuries, and high turnover. Challenges worsened by labor shortages during events like COVID-19, making automation in this step not only desirable, but necessary. At the core of this system is a customized dual jaw gripper, capable of independently controlling two opposing jaws to securely grasp both legs of the chicken. This design enables flexible manipulation strategies, such as grasping one leg at a time. Furthermore, an eye and hand camera is mounted between the jaws to provide a clear visual perspective for observation and vision-based policy training. This animated plot visualizes the real-time behavior of both jaws during data collection stage. The top trace shows the left jaw's state, while the bottom shows the right jaw. Each signal dynamically switches between 1 for open and 0 for closed. As the demonstration progresses, we can see how the gripper responds to input commands, closing or opening each jaw independently, depending on the position of the chicken legs. These binary state signals are logged frame by frame alongside proprioceptive and visual data, which form an important part of the training data set for our diffusion policy. These are the chicken samples used in our study. They were randomly purchased from local grocery stores. 10 were used for collecting demonstrations. These form the scene set. 4 others were reserved for evaluation only. These are unseen during training. This rollout shows a successful autonomous grasp executed by the trained policy using the ChicGrasp system. The dual jaw gripper, guided by a diffusion policy trained on human demonstrations, identifies the pose of each leg and grasps them sequentially without any human intervention. Here we present several rollout examples of the ChicGrasp system operating autonomously using a diffusion policy trained from scratch. Each of these images captures a successful instance of the robot identifying and grasping both legs of the chicken using its dual jaw gripper. While the diffusion policy achieved many successful grasps, there were also failure cases. In these instances, the gripper either failed to align with one or both legs or did not close the jaws correctly despite reaching the right location, resulting in incomplete or missed grasps. Now, we evaluate how the diffusion policy performs on the 4 unseen chickens, which were not included in training. This first group shows the baseline behavior with no added disturbances. Despite chicken samples being new, the policy generalizes well and produces successful grasps. In the next test, we introduce an external disturbance by manually pushing the chicken downward, just as the robot is about to grasp. Even with this interference, the policy reacts effectively, realigning and completing the grasp. Here we simulate environmental noise by introducing vibration to the table. Despite the shaking motion, the diffusion policy can complete the grasp. This next set involves a combination of test conditions: camera occlusion, low lighting, a wet surface, and leg separation. All of these trials succeeded. This suggests that the policy has learned adaptive features, not just memorized training examples. Of course, not all evaluations succeeded. Here we show failure cases from the same disturbance categories. The policy fails to align or close the jaws correctly for evaluation cases such as camera occlusion, low lighting, and leg separation. To better understand failure modes, we created a taxonomy across methods. For diffusion policy, the most common failure was slip-on lift. where the grasp is correct, but the chicken slips out during lifting. Other failure types include approach stalls, no closure, and collisions. LSTM/GMM failures were mostly due to not closing the jaws. IBC failures were largely erratic and unstable. Here we demonstrate failures across unseen disturbance conditions. Conditions like lights off and leg separation cause the most failures. Overall, this chart highlights which external factors are most challenging and where future improvements, like tactile sensing or feedback control, should be focused. To benchmark our approach, we also trained an LSTM/GMM model from scratch on the same chicken grasping task. As shown in these rollout examples, the LSTM/GMM policy was relatively stable in navigating to the correct grasping location. However, it consistently failed to close the jaws, resulting in unsuccessful grasps. We also benchmarked the IBC algorithm, trained from scratch on the same grasping task. As seen in these autonomous rollout attempts, IBC frequently failed to produce stable or successful grasps. The jaw trajectories often lacked precision and failed to align with the legs of the chicken. We evaluated three methods: diffusion policy, IBC, and LSTM/GMM, across 14 chicken samples, which were randomly purchased from local grocery stores. Each method was tested in 140 pick and rehang trials, including 4 disturbance cases. Diffusion policy completed 113 out of 140 trials, achieving a success rate of 80.71%, with each trial taking approximately 28 seconds to complete. On the other hand, IBC and LSTM/GMM failed all 140 trials. Due to a timeout, each trial was terminated at the 60-second mark because the initial pickup was never achieved. These results demonstrate the effectiveness of the diffusion policy in handling deformable bioproducts.